Hello children, welcome to Zero Panic Maths. In today's session, we are going to start with a new chapter, Chapter 2, Polynomials. Okay, in this chapter, we are going to see the different kinds of polynomials, different features of the polynomial, and finally, some important geometrical characteristics of the polynomial. Okay, so let us start with the definition of the polynomial. As you all know, the word poly means more than one. You already know this because you have studied this in your previous years. Okay, more than one. So as the name indicates, polynomial is an equation with more than one term. Okay, you can say it is an equation with more than one terms. Okay, more than one term. So it's a simple definition of that. So any equation that has more than one terms, say for example ax plus b, ax square plus bx plus c. We are going to see all these different terms of different kinds of polynomials in our next discussions. So to simply define a polynomial, polynomial is an equation with more than one terms. Okay. Okay, now uh, let us define some features of the polynomial. Okay, so if p of x, if you are defining any polynomial by p of x and that is a polynomial in x, okay, so that polynomial can have any different kind of what you call as variables inside it. Okay, so a polynomial, if it has the variable x in it, it is called as p of x. If the polynomial has a variable y in it, that can be called as p of y. Okay, in that way you can define the polynomials with different kinds of variables in it, and that is called as a polynomial with that particular character inside it. Okay, so we are defining in generally, if p of x is a polynomial in x, then the highest power of x in p of x is called as degree of the polynomial. Okay, so an example given here is, see, for example 4x plus 2. Now, as I have already explained to you that an equation with more than one term is a polynomial. So this is a polynomial with two terms inside it, and those two terms are actually 4x and 2, and those two terms are separated by an operation. Okay, separated by an operation. Usually these operations are plus and minus only. Okay, so okay, that is more depth discussion on the polynomial, but what we have to understand here is what is the degree of a polynomial. So if suppose p of x is a polynomial in x, so we are taking an example of 4x plus 2, it is a polynomial in x, then what is the highest power of x in this equation? Okay, in this polynomial, what is the highest power of x? It is actually x to the power of 1. Okay, so that highest power of the polynomial is actually called as the degree of the polynomial. So what is, for in example 1, what is the degree of the polynomial? Is degree 1, because we have the polynomial with power in x as 1. Now similarly with example 2, what is the degree of this polynomial? This is a polynomial in y. So y is appearing in two terms here, and y with exponent as 1, and y also has an exponent or power as 2. So the highest power of y in this equation is the degree, and the degree of this polynomial 2y square minus 3y to the power of 1, or you can call it as 3y plus 4, is a degree 2. Now similarly, since I've already defined what is the degree of this polynomial, this is again a polynomial in x, and the degree of this is 3, because you see there are three terms with x are appearing in this polynomial, x with power 1, x with power 2, but x with highest power is 3. So it is called as a polynomial in x with degree 3. Okay, don't look at the square roots and all, those are all the constant terms. Okay, now since it is a simple definition of what is a polynomial and what is the degree of a polynomial, hope you understood this concept. Now let us look at some of the examples where the equations are not called as polynomials and what are the reasons for those. Okay, now some of the examples, I've taken two examples here. The example square root of 2 plus, sorry, square root of x plus 2 is not a polynomial. 1 divided by x minus 1 is not a polynomial. Now why these are not called as a polynomials? Because polynomials have some important features. Okay, what are those features? The degree of a polynomial should be always greater than or equal to 0. It means that the degree of a polynomial is always a whole number. It can be 0, but it should be 0, 1, 2, 3, 4 positive natural numbers only. So it is a whole number altogether. So it cannot have the fractions as its powers. Okay, because of course fractions are not part of the whole numbers. So here in this example, if you see, what is this? Square root of x plus 2. It is a polynomial, sorry, it is an equation with two terms, but it is not called as a polynomial because it does not satisfy the characteristic that the power of a variable in this is not whole number. What is the power of this? Square root of x should be can be written as x to the power of 2, x to the power of 1 by 2. Okay, I'll explain this in the next coming sessions, how exactly the square root is written as 1 by 2. 1 by 2 is a fraction and not as part of the group of whole numbers, so it cannot be the polynomial. And again, another feature is the power of x or the term x should not appear in the denominators. Okay, even you cannot call 1 by x also as not a polynomial, because if you just write x, this will become x to the power of minus 1. Okay, and again minus 1 is not a whole number. So what are the features of a polynomial? What are the features of an equation to become a polynomial is that should have a degree with whole numbers. Starting from 0, the positive numbers are only the powers can only become the powers of the variable in the polynomial. And what are those important features? First feature, okay, let me write that, the three important features. You need to just remember this. Okay, first is the degree of a polynomial should be always whole number. Okay, just make a note of it and keep it in your mind. Okay, it should be whole number. So since it is whole number, actually this is the second feature is actually based on the first feature only. Since it is a whole number, it cannot have negative degrees. Okay, no negative degrees. Okay, no negative degree. Similarly, no fractional parts or no fractional degrees. You can say no fractional degree. Okay, and also okay, this is no negative degree only, no fractional degree only. Okay, so these are the features that you can remember. So remember that any equation in some variable x is called as a polynomial if the degree of that variable or degree of that polynomial is a whole number. Okay, so this is about the introduction of the polynomial. Okay, now let us see some of the important different kinds of polynomials. Okay, now knowing what is the degree of a polynomial, we can actually categorize the polynomials into different types based on the degree of a polynomial. Okay, now to start with, a polynomial of degree 1 is called as a linear polynomial. So what is a polynomial with degree 1? An example is a polynomial. This is a polynomial in x with degree 1. Okay, it is also a polynomial in degree with degree 1. don't look at the square root of 3. Okay, so square root of 3 actually is still the 3, number 3, which is a coefficient of x only. X still have the power as 1 only. This is a polynomial in y with degree 1. Okay, so in generally we can say that the polynomial, the linear polynomial is represented by ax plus b, where a and b are real numbers. Okay, you can see this. Okay, this is an important feature of linear polynomial. So any equation of the form ax plus b, where a and b are reals and x is a variable, of course, and also a is not equal to 0. A should not be equal to 0 here in this equation, because if a becomes 0, the whole term ax becomes 0, and that will not be an equation of degree 1 in that case. So that is the reason a should not be equal to 0. Okay, so this is a linear polynomial. So what is a linear polynomial? Linear polynomial is a polynomial of degree 1 of any variable. Okay, now similarly, going to the next kind of a polynomial, polynomial of degree 2. As you all know, quadrate. Okay, the word quadrate means square or with power 2. Okay, that kind of equation is called as quadratic polynomial. Quadratic polynomial is an equation in any variable with highest power as 2. Okay, so you can see an example here: 2x square plus 3x plus 2 by 5. Okay, y square minus 2. You can see these two examples. What is the difference here? In these two examples, this is an equation with three terms, where x to the power 2 uh, is the term that decides the degree of a polynomial, that is quadratic polynomial. And also you can see the generic definition of this. What is the generic form of a quadratic polynomial? That is ax square plus bx plus c. Here the terms are getting increased. Here it is only ax plus b, two terms. Here it is ax square plus bx plus c. So a, b, c are again the real numbers only, and having a not equal to 0. We are having that condition a not equal to 0 here also, because making a is equal to 0 will make this term x square as 0, and that will become, so if it is bx plus c, that will become a linear polynomial. Okay, that is the reason we are having that condition. And also observe that we are saying a, b, c are real numbers. That is the reason 2 by 5 in constant term, or 2 by 5, or any fraction in coefficients of x square are allowed, because those are all real numbers. Okay, and in addition to that, you should have a condition that a should not be equal to 0. Okay, here a is a coefficient of x square, b is coefficient of x, and c is a constant. Here in linear polynomial, a is the coefficient of x and b itself is a constant. Okay, now in this equation you might observe one thing, that y square minus 2. So you might be thinking that it is having only two terms. Okay, of course it is having only two terms, but the highest power of that variable in that equation is 2. So that is the reason it is called as a quadratic polynomial, and it is actually written as y square minus or plus 0 y and minus 2. So you can say this is the actual form of this equation, and the coefficient of y, which is b in this case, is 0. A is 1 and c is minus 2. Okay, okay, now let us go to the next definition, that is polynomial of degree 3 is called as a cubic polynomial, because you know that the word cube means of power 3. Okay, so any equation of the form in general, now you observe here the coefficients are getting changed by the type of the polynomials. So a is now becoming the coefficient of x cube. Okay, because uh, power 3 actually decides the type of the polynomial here. Ax cube bx square plus cx plus d. Here d is the constant, c is actually the coefficient of x, of power 1, b is the coefficient of x square, and a is coefficient of x cube. Again, a, b, c, d are all real numbers, and a should not be equal to 0 is the condition. Now let us take an example here. Again, you can see it has only this equation is an example of cubic polynomial with two terms only inside it, but you can observe that x cube is the highest is the term having the highest power in x. Similarly, this is another example of the cubic polynomial having a is equal to 3, minus 2 is b value, and 1 is value c, and minus 1 is the value of d. So this is all about the different kinds of polynomials, and the definition of the different kinds of polynomials is based on the degree. Degree 1, linear polynomial. Degree 2, quadratic polynomial. Degree 3 is cubic polynomial. Okay, hope you understood this concept. Okay, let us move to the next. Okay, now having any polynomial. Okay, now before we move to this definition, let me give some examples and let us understand what exactly is the value of a polynomial. Okay, let us take the example of 2x minus 3. Let me write it here, 2x minus 3. Now suppose if I put x is equal to 1, what it will be? 2 into 1 minus 3. So 2 into 1, 2 minus 3 is actually minus 1. Okay, now suppose I put x is equal to 4, what it will be? 2 into 4 minus 3. 2 into 4, 2 4s are 8 minus 3. And what will be the value of that? 5. Okay, so actually when I put some value into the variable x, that x is actually is replaced by the value that I am putting into that equation. Okay, now suppose this is called as p of 5. If p of x is actually the polynomial, so how can I represent this? Is p of minus 1. I'm actually replacing x by that given value. So this is called as the value of that polynomial. When some value, some real number value is put into the variable, then that the value that you are going to get is actually called as the value of the polynomial. Okay, now why did I explain this? Because we are going to define some important concepts on the value of the polynomial. So what exactly is a polynomial? The value of a polynomial p of x at x is equal to k. So in generally, where k is a real number, k is any real number, if you are replacing x by k, then the value obtained by replacing x by k is actually denoted by p of x, and that actually is called as a value of a polynomial. So how do we define? If p of x is a polynomial in x and if k is a real number, then the value obtained by replacing x by k in p of x is actually called as the value of a polynomial p of x. Now example, I've already given an example, but let us take another example of this. X square minus 3x minus 4. Suppose if I am putting x is equal to minus 1 in this equation, what it will be? So let us take an example, x square minus 3x minus 4, right? X square minus 3x minus 4. If I'm putting minus 1 in the form of in place of x, that will be actually p of minus 1. Okay, p of minus 1 is equal to minus 1 square minus 3 into minus 1 minus 4. What is minus 1 square? Is 1, minus 3 into minus 1 is plus 3 and minus 4. It is 1 plus 3, 4 minus 4 is actually 0. Okay, similarly, if you put x is equal to 4, that also is going to get 0 only in this equation. See, 4 square is actually 16, and 3 into 4 minus 12. Minus 12 minus 4 is minus 16. 16 minus 16, it is going to give you 0 only. Okay, so Now why I'm defining some values, the k values, which are giving us the 0 as the actual value of the polynomial, because that is called as 0 of a polynomial. Now we are going to define another feature of that polynomial, that is called as zeros of a polynomial. Okay, now you have seen what exactly is the 0 of a polynomial. So simply, a real number k is said to be 0 of a polynomial, 0 of a polynomial if p of k is equal to 0. Okay, suppose if you are taking some value and putting it into a polynomial, and if that value if that real value is actually making the whole polynomial's value as 0, then that actual k is called as 0 of a polynomial. Okay, so uh, here in this equation, for this equation, x square minus 3x minus 4, x is equal to minus 1 is a 0 of a polynomial, because by putting minus 1 into this polynomial, we are going to get the whole equation's value as 0. So that is a 0 of a polynomial. Again, by putting x is equal to 4, we are going to get 0 as the value of the whole polynomial. So that is also one of the 0 of a polynomial. Okay, so now how do we find the 0 of a polynomial? How do we find the 0 of a polynomial? So that is very simple. You should actually start with equating the given equation to 0 and solve that equation. Okay, by there are different methods to solve that equation. So if you solve that equation for equating the given equation to 0, then that will actually give you the actual value that makes the polynomial 0, and that is the way to find out the 0 of a polynomial. So simply I can just give you an example of a linear polynomial 2x plus 3, how to find the 0 of a polynomial. Okay, so let us just check how do I find the 0 of a polynomial. Okay, take an example, 2x plus 3 and equate it to 0. Okay, now solve this equation. 2x is equal to minus 3. Then what is x? Minus 3 by 2. Actually, what is 0 of a polynomial? What did we define? That by putting this value into the given equation, the whole equation's value becomes 0. Okay, let us verify this by putting minus 3 by 2 in place of x, whether the equation is going to be 0. Yes, you can see that minus, so it will actually become 2 into minus 3 by 2 plus 3, right? So 2 get cancels, and minus 3 plus 3, it is going to give us 0. Okay, now by defining or by finding the 0 of a polynomial in this way, you have actually defined one important feature, that in general, you observe this carefully. Okay, in general, if k is a 0 of p of x, which is equal to ax plus b, linear polynomial only we are defining, which is ax plus b, then pk is equal to ak plus b. Actually it is, we are just replacing x by k and equating that to 0. Then the k value is always going to be minus b by a. You can observe this here. What is minus 3 by 2? See, what is ax, what is 2x plus 3 here? If you equate that to ax plus b, what is a? It is 2. What is b? It is 3. Correct? So minus 3 is actually minus b, and what is 2? 2 is a. Sorry, 2 is, okay, let me write this, minus b by a. What is b? B is actually the constant term in the generic equation ax plus b. Where is that? Ax plus b. B is a constant term and a is coefficient of x. So in general, for a linear polynomial, ax plus b, the zero of a polynomial is always minus b by a, where b is a constant term and a is a coefficient of x. So that is what generally we are defining. Zero of a linear polynomial ax plus b is minus constant term divided by coefficient of x. Okay, hope you understood this concept. Okay, let us verify the same zero of a polynomial for a quadratic polynomial. Okay, okay. Now, before we go for the zero of a polynomial for a quadratic equation or quadratic polynomial, let us just test the geometrical meaning of a zero of a polynomial. Okay, it is for linear polynomial only. Here you can observe one important feature of a linear polynomial, that if you plot a graph of a linear polynomial ax plus b, y is equal to ax plus b, then that graph is always going to be a straight line, and that straight line passes through some points. Let us verify that by plotting the graph of a linear polynomial ax plus b. We are taking an example of 2x plus 3 here to plot that graph. Okay, let us take two examples by considering x is equal to minus 2. Okay, you can take any example, but I'm taking two values for that x, minus 2 and 2. Okay, and remember, these two values are such values which may or may not give the value of a polynomial as 0. Okay, let us find out the value of y is equal to 2x plus 3 by putting the two values minus 2 and 2. Now if I am putting x is equal to minus 2, then 2 into minus 2 plus 3, it is minus 4 plus 3 and equal to, what is that equal to? Minus 1. So I'm writing minus 1 as the value of y is equal to 2x plus 3 in case of minus 2. Okay, now similarly y is equal to I'm putting plus 2. Okay, that is actually 2 into 2, which is 4, plus 3, which is equal to 7. Okay, I've just solved this equation just to verify these 2 points. Okay, what are those 2 points? Minus 2 and minus 1, 2 and 7. Okay, we're going to plot the graph for these two values and see whether that graph gives us a straight line. Okay, and based on that we can actually find out the zero of a linear polynomial. Okay, let us see that in the next slide. Okay, now here you can observe that if I am plotting a graph for the given table, now let us point out the points minus 2, minus 1 and 2, 7 on this graph. Minus 2 is the value of x and minus 1 is the value of y-axis. Remember, so this is that point. I have actually already pointed out this point. Okay, minus 2, minus 1. You see this? Minus 2 is actually the x point and minus 1 is the y point. So if you actually make a crossover of these 2 points, you will get this point as minus 2, minus 1. Similarly, this is 2 x-axis and the y value of 7, it is 2, 7. Now let us draw a straight line connecting these 2 points, minus 1, minus 2, minus 1 and 2, 7. Okay, okay, let me take the ruler for that. Okay, so let us keep this. Okay, so if I draw a line, okay, so this is a line that actually is connecting the 2 points 2, 7, minus 2 and minus 1. Now you can observe this line is a straight line. Now of course you might think that we have taken only 2 points. Even if you take more than 2 points also, this is always going to be a straight line. But the important thing that you should observe here is this straight line with these two given points is actually intersecting the x-axis. You should observe that point where exactly it is intersecting or cutting the x-axis, and that point is minus 3 by 2. It is actually intersecting this point between minus 1 and minus 2, which is actually minus 3 by 2, which is 1.5. Okay, minus 1.5, it is half of that, and y value for that coordinate is actually 0. Okay, so this point where the straight line for the given equation y is equal to 2x plus 3 cuts the x-axis or intersect the x-axis is actually called as the zero of a polynomial. Okay, so for any linear polynomial, if you plot the graph of that, it is going to be a straight line, and that straight line is always going to cut the x-axis at one point, and that point is going to give us the zero of a polynomial. So we have already seen by solving the equation 2x plus 3, it is going to give us the 0 as minus 3 by 2. Okay, and for that the y value will become 0. So what are the observations? The 0 of a polynomial 2x plus 3 is the x coordinate of the point where the graph of y is equal to 2x plus 3. This is actually y is equal to 2x plus 3. This graph is actually 2x plus 3 intersects the x-axis. So it is intersecting the x-axis at point minus 3 by 2 and 0. So in general, for any linear polynomial ax plus b where a is not equal to 0, the graph of y is equal to ax plus b is a straight line, first point, and that intersects the x-axis exactly at one point. It is always going to intersect the x-axis at one point only, and that point is always minus b by a. We have already verified that also. Minus 3 by 2 is actually the minus of a constant term divided by the coefficient of x, that is minus b by a, and the y coordinate of that is always going to be 0. It means that finally you have to keep in mind that it means the linear polynomial ax plus b where a is not equal to 0 has exactly 1 0. So that has only one value, that makes the polynomial as a 0 for a linear polynomial. Okay, now let us move to the next. So 0 of a quadratic polynomial. Okay, now in the same way that we found out the 0 of a polynomial for a linear polynomial by graphical method, we have to find out the 0 of a polynomial and how does the graph of a quadratic polynomial behaves. Okay, now y is equal to ax square plus bx plus c is a generic form of a quadratic polynomial that you know already. Now let us take the example of y is equal to x square minus 3x minus 4 as one of the equation, and that is going to give us a parabolic curve. Okay, let us see that whether it is going to give us the parabolic curve or not. And that parabola is actually like this. It is going to give us the equations like this, the graphs like this. Either the parabola will be in the upward direction or in the downward direction like this. Okay, let us see. Okay, now let us have some examples, some values, and find out the y values. Some values of x will find out the y values. Say for example minus 2 minus 1. So for x is equal to minus 2, what is y value? What is y? Y is x square minus 3x minus 4, right? Okay, for x is equal to minus 2, it is minus 2 square minus 3 into minus 1 minus 4. Minus 2 square is 4, minus 3 into minus 2 is plus 6 minus 4. So the value of this is going to be 6 because minus 4 minus plus 4 get cancels and y is equal to 0. See here in this table you can observe for some of the values the y value is actually getting 0 also, and we are considering for those values also we are considering for the graph to be plotted. Okay, now For minus 1, it is going to give us 0. The same example I think we have seen already, that if putting minus 1 is going to give us 0. So in this way, I've taken some examples of x and found out the values of y. Let us plot the graph for that. We are not going to verify all these values for x, because that is not our intention. Our intention is whether when we plot the graph for a quadratic polynomial, whether it is going to give us the parabolic structure or not. Okay, let us see that. Okay, now again, as in the previous example of a linear polynomial, I've taken a quadratic polynomial ax square plus bx plus c. Okay, and this is the example of that. We have the table already ready to be plotted, and we will see whether it is going to give us the parabolic curve or not. Okay, now let us plot the points minus 2 and 6. Minus 2 for x-axis and y-axis is 0. So this is that point, minus 2, 6 plus 6, the first point. Minus 1, 0. Minus 1, 0 is the second point. Okay. For 0, it is going to give us minus 4 as a y-axis value. Okay. So this is that minus 4. Let me hide this. Okay. So 0 minus 4. Okay. 0 minus 4 is the third point. 1 as x-axis and minus 6 as the y-axis value. Similarly, 2 minus 6, the fourth one. Fifth, 3 minus 4. 3 minus 4. X value 3 and minus 4 as y value. 4 as x value, it's going to give us the y value as 0. That is actually the 0 of a polynomial. Now 5, 6. 5 positive x-axis and 6 positive y-axis. Okay, now if you connect all these points, you cannot connect this with a straight line, because you can observe this here, all these points cannot be connected with a straight line. So if you start just writing, okay, just drawing a line over here by connecting all these points, it is actually going to give us a parabolic structure. Okay, so that is the reason we say that any quadratic polynomial, when drawn on the graph for some points, then that is going to give us a parabolic curve. This parabolic curve is in upward direction, but you can have, for some values, you can have the parabolic curve facing downward direction as well. Okay, now what is the thing that we need to observe? Where is that x-axis point where this parabola is cutting the x-axis? Because those 2 points are our zeros of a quadratic polynomial. Zeros of a quadratic polynomial. So one point is minus 1, 0 is one point where it is cutting the x-axis, though it is a minus x-axis, but it is cutting the x-axis here. Another point is the positive side of the x-axis, where it is cutting the x-axis at 4, 0. Okay, what did we observed is the parabola curve for y is equal to the given equation is actually cutting the x-axis at 2 different points, minus 1, 0 and 4, 0. Okay, so what is the observation? Minus 1 and 4. Okay, because the value of those points, the y value of those points are zeros here. Okay, minus 1 and 4 are the zeros of this polynomial. Okay, now you can observe that here for minus 1, the y value is actually 0. For 4, the y value is actually 0. Okay, mathematically also we actually know that minus 1 and 4 are the zeros of this quadratic polynomial, and graphically also, if we plot it here, those are the same points that we are going to get by observing that whether those points are cutting the x-axis at the given values. Okay, so that is by mathematical solving the mathematical equation we are going to get the zeros, and this is how we are going to get the zeros of a quadratic polynomial by plotting a graph. So what is the observation? -1 and 4 are the zeros of this polynomial, and these are the x coordinate points where the parabola y is equal to the given equation intersects the x-axis. That you can observe here. This is one point, this is second point. And the important final point that we need to observe is, for a quadratic polynomial, ax square plus bx plus c, where a is not equal to 0, has at most two zeros. At most two zeros. You might have observed that for a linear polynomial, how many zeros were there? Only one zero. For any given value, for some given value, it is going to satisfy the equation for 0 with one value. For quadratic polynomials, there will be two values for which it is going to be, the whole polynomial value is going to be 0. So at most two zeros. It might have only one zero also, quadratic polynomial, but at most maximum it is going to have two zeros only for a quadratic polynomial. So that is what the observation that you should see here. Okay. Okay, now let us move to the next session to verify some of the features of this. Okay. Okay, now let us verify some of the important cases of intersecting x-axis. Here in this section, we are going to see the different ways in which the parabola representing the quadratic equation is going to cut the x-axis or intersect the x-axis. So what is that? The case one. The case one is where the parabola, either the downward direction or upward direction, is going to cut the or intersect the x-axis at two different points, and those two different points are A and A dash. Okay, see, and it is going to cut the 2 points. The 2 points either at the positive side A dash, these are the 2 points. If one is positive side and one other is negative side, as we have seen in the previous example, okay, one zero is going to be negative side and another zero is going to be the positive side, or you might also get the two zeros are positive values only. The second case is the parabola is actually going to touches it, you're going to get the zero as only 1 0. Okay, so the example is, if the parabola just touches the x-axis from downward side or from the upward side, if it just touches it, then A is the only point where you're going to get the whole polynomial value as 0. So it is going to give us only one 0 of a polynomial. Okay, because we know that it is going to give us at most two zeros for a quadratic polynomial. So case one, where the parabola intersects the x-axis at two different points. Case two, the parabola just touches the x-axis and cuts the x-axis at only one point. Okay, so next we are going to see, okay, now there is another case where a polynomial might not have any value that makes it 0, or there are no zeros at all. Okay, has no zeros. What is that case? If suppose the value taken by us makes us to plot the graph like this, or downside, it is not actually not even touching the x-axis nor even intersecting the x-axis. So the graph is completely above x-axis or completely below the x-axis, in which case the polynomial has no zeros. So in general, the polynomial of degree 2, which is called as a quadratic polynomial, has at most two zeros. So by all these cases, why we have seen all these cases? Because by all these cases, the graphical representation, we observed that the quadratic polynomial is going to have at most two zeros only. So finally, continuing in the same manner, okay, by plotting the graph for the geometrical representation of cubic polynomial, okay, polynomial of degree 3, okay, I'm not going to plot that graph, okay. So we can say that, or we can arrive at a point that it will have at most three zeros, because for linear polynomial at most one, for quadratic polynomial at most two zeros. So continuing in the same fashion, we are going to get for cubic polynomial at most three zeros. It might have one zero, two zeros, or three zeros, or it might not have zeros also, no zeros, but at most three zeros for a cubic polynomial. So the graph for that is actually given in the textbook. You can observe those graphs. Okay, that graph is actually going to give us the curves like this, where it actually cuts the x-axis at three different points. We're going to see some of the examples of this. So how do we find out the number of zeros of a given polynomial? Is how many times the plotted graph is cutting the x-axis. So based on that, the counting the number of points where the graph given graph is cutting the x-axis, we are going to decide what is the number of zeros of that polynomial. So in general, for a given polynomial p of x of degree n, okay, p of x of degree n, if you plot the graph y is equal to p of x, that is going to intersect the x-axis at maximum of n points and has at most n zeros. So if it is cutting the x-axis at 2 points, it is having 2 zeros. 3 points if it is cutting, it is having 3 zeros. Similarly, 1 point if it is cutting it, it is going to have 1 zero. So in generally, for a degree of n polynomial, it is going to have at most n zeros, and maximum at n points it is going to cut the x-axis. Now based on this concept, let us see some of the examples. Okay, it's very simple. uh, it is only one example given with the given graphs. Okay, look at the below graphs, and each of the graph that is plotted for y is equal to p of x, where p of x is a polynomial. They have not given what exact polynomial it is. We need to identify that what are the number of zeros for each graph. Okay, there are 6 different examples given here, and you might you can see it here, what is the degree of a polynomial, or based on that, what is the zero of a polynomial, number of zeros of a polynomial. So for case 1, you see that there is a graph that is plotted and it is cutting the x-axis at only 1 point. So what are the number of zeros for case 1? It is zeros, 1 0. Okay, for case 2, it is a parabolic structure and it is cutting the x-axis at two different points. So the number of zeros are 2. Okay, now similarly, this is an example of a cubic polynomial that I already explained to you. Okay, cubic polynomial is cutting the x-axis at three different points. Okay, and the number of zeros of that polynomial is 3. Okay, here there is one graph that cutting the x-axis at 1 point. So the zero of a polynomial, zero of this polynomial is only 1. So don't get confused with cutting the y-axis. Okay, it is only the line. If it cuts the x-axis, that point only should be considered as the zero of a polynomial, because for that point y will be equal to 0. So don't consider this point because this is y non-zero value. Okay, so here the parabolic structure touching the x-axis at 1 point. So the zero of these polynomials are only 1. Here the graph is actually cutting the x-axis at 4 different points. So what are the number of zeros for this polynomial? It is 4. It is actually a polynomial of degree 4. So it is cutting the x-axis at 4 different points. This is a simple example that you can understand from the given graph. Okay, now let us have some example. This is a solved example. We will have some exercise example also. So this is just similar to the solved example. By looking at the given graphs, we need to find out what are the number of zeros for these given graphs. Okay, let us have this. Okay, for case 1, let us write it here. For case 1, How many zeros? No zeros, because the line, the given straight line is actually not at all touching the x-axis nor intersecting the x-axis. For case 1, no zeros. So now, as I already told you, that an equation may or may not have zeros. So this is one such example. So at most one for polynomial of degree 1. So what is the zero of this polynomial? The count of zeros of this polynomial is actually 1 only, because it is cutting the x-axis at only 1 point. So second case, the value is 1. What is this? It is actually cutting the x-axis at 3 different points. So case 3 is actually 3. Case 4, it is actually cutting it is a parabolic structure, quadratic polynomial, cutting the x-axis at 2 different negative x-axis only. Okay, it is also one of the case, but cutting the x-axis at 2 different points, so it is 2. Okay, now very simple. 3, 4, it is cutting, this curve is actually cutting the x-axis at 4 different points. So what is the number of zeros of this polynomial? Is actually 4. How many number of zeros are there for this polynomial? 1, 2, 3. 3 different points. It is actually cutting the x-axis or intersecting the x-axis. So it is 3. 3. Okay. This is all about the exercise 2.1. Okay. Now let us stop this discussion here only. And in the next session, we're going to see some important relationships between zeros and coefficients of a polynomial. Okay. Thank you.